All right, welcome back. Welcome back to the channel. So in the last video, we have learned about how to fine tune Llama 2.0. So we have fine tuned Llama on a specific data set and used it, use the patterns that it has learned to actually use it for different problem. And we have, I think, solved the problem of chatbot or something. So in this video, as I have promised in the last video, we will be going in depth of the architecture of Llama, like what are the different components and the different ideas and the different changes that are done in this model. And essentially they are like not specific to this paper. This paper did I think, as per my knowledge, it did not introduce anything new, but it had a greater performance because it succeeded in combining different features of different models, and it has successfully worked very well. you know it has developed very small models, pretty comparatively small models, but with a very high performance metrics, right? So we are very small models with very less parameters compared to other language models in the industry. And they have these models actually have Llama has actually beat some models in terms of metrics, in some metrics. So we will be covering some main changes that have been introduced in this paper. So start off again, we're going to look at the same paper. Again, definitely would recommend you to definitely read everything line by line, but I'm just going to skip over. Yes, I have covered most of the part, I believe. The pre-trained data, like from which they have accessed their data. So the main part we'll be covering in this video is the architectural part, the part where we can understand the main changes that have been made in the architecture of the model. And again, I'm going to cover all of them, right? I'll just cover each of the changes that I have done. So the first change, so as you can see, so you can read everything. So so these are the main differences. The first difference, the pre-normalization trick. Again, nothing new here, right? We just use the RMS normalize function to normalize the input values. So before, for example, we'll have a transformer, right? We'll have a transformer in which we will just input like a bunch of token values or a bunch of sequence values, and we will get like QKV vector for each of the vector and or each of the word or each of the embedding, and then we'll perform the attention calculation, which you probably should have idea before getting into this video, right? So before passing the inputs through the attention mechanism, before performing the attention operations, what we'll be doing is we will be normalizing these values, right? Whatever embeddings we are going to have. So we're going to have a bunch of embeddings, right? We are going to have a bunch of embeddings with like different values, let's say. So what we are going to do is we are going to normalize these values, right? Just to make sure that they're on a very similar scale, that the embeddings have similar values, at least to some extent, and there is no huge variance in this data. We want the variance to be as less as possible. And if you remember about standard normalization, so the basic idea of standard normalization is to get the mean of the data to be 0 and standard deviation of the data to be 1. So how can we, so what is the problem with standard normalization, right? So as like if we get the mean to, so there are a bunch of disadvantages. There are a bunch of disadvantages of performing the standard normalization. That is why we perform RMS normalization. So if we have actually performed the standard normalization, we would have missed a lot of features, right? A lot of features would be missed, number one. And number two, I think so number one, that is a number one thing. And number two, we will be not let's say we will be missing some important values. We will be not giving equal importance to everything. We will be missing some important values, which again through an RMS normalization we'll be trying to solve this. So there's a specific formula that we'll be using. What we'll do, what we'll be doing is we'll essentially be calculating the mean, right? Just like mean, at least to some extent, but we will take value and just square all of them, right? As the name suggests, RMS, right? Root mean squared normalization. We're going to get the square of each value. So each embedding, we're going to add all of these values, right? I'm going to divide by n, and we'll just get the square root. That is the basic idea of what we'll be doing. So each signal, in a more sequential engineering way, right? A signal way. So each will take each signal and will essentially square the value, right? For like give like smaller values, will decrease the smaller values and increase the larger values. And if there are variance, we'll be essentially like capturing it, right? So we'll just get the each value, and we'll be squaring all of them, adding them, divide them by the number of samples, just like standard mean, but we are squaring each value, and then we'll be getting the square root. So that is the basic idea of what we'll be doing. And after calculating this, we'll just like, I think we'll just put in, let's say this is S, and then what we'll be doing is we'll be taking each of this embedding, let's say, and dividing this embedding by this S, right? So we'll be just performing this little operation through which we could actually scale the model into a um, specific range, right? Specific, um, you know, like threshold, right? We'll just scale these values, either decrease the values or increase the values as per the calculation. So that is the idea of RMS normalization. So I think we have completed the first part, the first change, the first major change that they have introduced. And the next change is using the Swiglu activation function rather than the ReLU activation. So what is the change? As you know, ReLU is a very common and a very popular activation function, right? Whenever you are like, if you have any experience like building uh, neural networks, you'll most probably use ReLU in the hidden layers, right? Will like even different problems, maybe transformers, and also you'll only use ReLU activation function because of its even though it is very simple, it is pretty simple, it does work well. So you will use ReLU, but in this paper, in this implementation, they have used an activation function called GLU, Swiglu. So we're just covering this paper. So this paper introduced Swiglu for transformers. They proposed that this will increase the performance of like a transformer, like what the transformer will actually doing. We will the performance of transformer. So this is the activation function. So essentially, what we'll be doing is, uh, rather than just, so this is not just like a activation function. This is a like a final hidden layer. So this is just like hidden layer in which we'll also have like learnable parameters W and V and B and C. So yeah, there are some learnable parameters, and for the same input, we'll be applying all these parameters for the same input. What we're getting is, after we get the output from the attention or the final linear layer, right? We'll be passing them through through this activation function, right? In which we are going to rather than just having like XW, only XW, we'll also be having another set of weights V and C. We'll be performing this also on X, and we'll essentially do perform element wise multiplication, right? We'll just calculate both of this. Again, V and C are learnable parameters, W and B are also learnable parameters, and then after performing these separately, we'll essentially be calculating the element wise calculation. That is actually, this is actually called as gated linear units. So this is like, I think, very pretty common in the case of deep learning. So what they have proposed is that they have come up with an equation. I think there's it is above. So they have come up with an equation, right? In which they will so this is the final equation. So this is the Swiglu equation, the one that we want. So if you I just get the equation of the Swiss activation function. So this is the activation function of switch. So after getting a value input, so we'll get a value as input. We'll be multiplying x into sigmoid of beta x. So beta is a learnable parameter, right? So we have another learnable parameter inside the switch activation function, right? I just want to you know what? I'll just write it. So this is the switch activation function. We'll be taking f of x. Sorry. So we take, so this is the f of x activation function, switch activation function, right? So what we'll be doing is we'll be multiplying x times the sigmoid of beta x. Yeah, so beta x. So this is switch. And what is Swiglu doing is, so we'll be combining this switch activation function with another learnable parameters, with some more learnable parameters, which you will see. So we'll just getting the switch of xw. So we'll be multiplying w and x. So w is a weight, right? So we're multiplying w and x and pass them through switch activation function. We'll be performing element-wise multiplication on xv, and then again we'll be performing w2 on top of that. So essentially, we'll be having a pretty complicated version of the gated linear unit, but something that definitely works. So here we have like 3 weights because we are performing attention here, right? We are performing transformer, right? So therefore we'll be having 3 weights, right? And then we'll be essentially performing this specific function, right? We'll be getting the switch activation function, and then passing the x into w into that switch activation function, and essentially multiply that by xv and multiply that by w2, right? So this is the activation function that we will be using inside um, llama, right? And we have many variations, right? RAGLU, reglu, and bilinear GLU and all that. And in this paper, in this specific paper, Swiglu is used as the activation function. I don't know if I should pronounce it like that. I don't know if that is the correct pronunciation, especially looking at the capitalization or the specific capitalization. But for now, I'll just call it as Swiglu. No, not like, why not, right? So the next big change is using of rotatory embeddings. They have used something called rotatory embeddings, which we'll definitely cover. So this is the paper which I have introduced rotatory positional embedding, and the idea is actually pretty simple and intuitional. It is very intuitional. So so this is the paper, ROFormer, ROFORM here, rotatory positional embedding for transformer. So the idea is that, so you know about positional embedding, right? So again, a lot of things, you can just skip everything here, a lot of main things. So this is called absolute positional embedding, right? In which we are going to have, like, we're going to calculate sine of k by 1000 2t by d. You know it, right? In attention, while we are performing attention, in order to make the model, um, aware of the position of the text of each word. So we'll be taking each word embedding, and then we'll be adding the positional embedding in order to increase awareness of the model based on the position of the word. So the model will understand the position of the word based on so using this positional embedding, right? So we'll be calculating these positional embeddings, and the problem is that every positional embedding, so this is absolute, this is not relative, right? This is absolute. So there is only like one positional embedding for like no, this is not relative, so it does not, like, the basic idea of attention is actually getting the attention between two values. So attention is actually relative, but here it is not carried out in a relative process. This is pretty absolute. So each word will have like a specific positional embedding, and it does not have links between different words and all that. So what we are going to do is we are going to solve that problem. So essentially, so we have a lot of mathematical equations. Definitely, I definitely recommend you to go through them. Essentially, they're just the product of Q and K, right? You know, query and key value. So they have come up with this equation, right, in which they're going to take the xt, and then they're going to multiply that by the query vector, the key vector, and the xn, right? Xn, I think, corresponds to the key value, the word for the key, right? And then we're going to get the query value, the current query word. So what the query word is, we're going to multiply that by wk, wq, and p of m minus n. So here p of m minus n is actually the relation. So the relation. So p of m minus 1 is actually the relative positional embedding between q and k, right? So we are going to have a relative positional embedding between q and k. So essentially, at while we are calculating this sum or this product for each of these values, so we're going to take each combination and we're going to perform this, right? At that time only we are going to calculate the positional embedding. So the positional embedding is going to change for each calculation, and we get, even though we are making this a little complex, the model is actually going to be a little more complex because we have to calculate p of m minus n also, right? We are also going to calculate that, but still the performance increased. So there is a like pretty good increase in performance. So therefore this embeddings are actually used. So there are actually, again I'll try to revise. So while we are calculating each product of this q and k, when we reach calculating q into k, we are essentially so getting the positional embedding. So we are going to change the positional embedding for each calculation. So we are going to get a new positional embedding which defines the positional relation between the query word and the keyword. And then based on that, the model could actually understand positions better, right? So that is the main idea of using rotatory embedding, right? So that is the main idea of using rotatory relative positional embeddings, right? Which are relative to each other, not like equal, but relative. So that is relative. So that is relative positional embedding, right? And we have bunch of calculations, general form, and all that. They have derived it. So this is how we calculated. So these are the formulas. There are a bunch of formulas and all that. You could just go through them if you want to. So they also have the derivation, which is actually quite nice, and the theoretical explanation also, long-term decay and all that. So therefore, if you are into like mathematics and all that, if you are interested, please check out. And for the next big change that they have made, it is optimizer side. They have changed the optimizer, right? Using the Adam W optimizer, right? So again, you should have known about Adam, what Adam actually is. So essentially, we have many gradient descent algorithms, right? So like we use these algorithms to update our weights, and there are many algorithms. So there are many terms and factors that are coming out with each optimizer. So the specialty as of Adam is actually you could add momentum and all that, right? So that is Adam. So it is actually one of the main most used um, optimizers you could go through. I have found this very amazing blog, pretty good blog, through which you could actually understand everything. I think I'll provide the link to this blog in the description. Make sure to check that out if you are interested, right? So essentially, Adam W is actually we add like weight decay. We'll be adding weight decay. So we'll be just covering what that means. But yeah, so that is why it is actually called as weight decay. So okay, I'll just go through the paper, or let me just. Oh, sorry for that little problem, right? So the main change that we're making in Adam W is that we'll be adding a weight decay. So what is weight decay? Well, it is something we used to prevent overfitting. So what we'll be doing is in Adam W, we'll be having the parameters, right? We'll be having the parameters which we'll be calculating through like gradient descent. We'll be performing the chain rule. We'll be using the chain rule. We'll be calculating the derivatives, and after calculating the derivatives, right? What we'll be doing is we'll be essentially um rather than just multiplying, just rather than just performing a change, rather than just subtracting the parameters and all that, or subtracting the derivatives and all that, what we'll be doing is we'll be having a weight decay. Weight decay. So we'll be having a parameter called WD, let's say, and this is a hyperparameter. And based on this parameter, so this is a factor for how much weight decay we want to have, how much we want to perform. So the main goal of weight decay is actually to prevent overfitting. So let's say you have training data, right? Let's say you have training data in which a specific pattern is carrying on. So there is a specific complex pattern is carrying on. That does not necessarily have to be happening in the real time. So let's say, for example, you collect some data. I hope you are comfortable with overfitting. Even if you're not, I'm just going to cover what that is. So let's say you have some, let's say you're trying to do some text classification, or let's say image classification, or text classification, let's say. So you have some sentences. So let's say you have all the sentences begin with, let's say, letter W or Y, right? That is common, right? So all the questions so let's say you're building a chatbot and all the question in your sentence starts with Y. You don't want a model to actually learn every feature. You don't want a model to learn that every question starts with Y, right? Because it doesn't. And maybe there are some outliers, right? We don't want the model to overfit and try to create patterns sort of randomness, essentially. So therefore, that is overfitting. In even language modeling, we are going to face scenarios, overfitting scenarios. So therefore, in order to decrease that, we will be having a weight decay. So this is going to be the factor through which will decrease the changes. So the changes that we'll be performing. So while training, we are going to change the weights, right? So the change we are going to performing is essentially controlled by this weight decay hyperparameter, and using this, will actually reduce overfitting. And also, if our parameters are like huge amount of values, so let's say we have huge gradients, right? We have very high gradients. That is going to cause our model to actually not get to the global minima, not reaching the optimal point, or not reaching the point of convergence. It is going to we're going to make like huge changes, which is going to reduce the stability of our model. So in order to solve the problem, we are going to have weight decay, right? While we are um, updating the weights in order to solve these problems of reducing the overfitting, and also reducing the um, sizes of the gradient. So that is the main goal of this Adam to W. So essentially, I think it's like even talking about this is out of context. Like we are talking about language modeling now. It might be pretty out of context, but I just take this as an opportunity to tell you about Adam W optimizer. And yeah, as you can see, so these are the performance metrics, right? So Llama did have higher performance, like specific or all metrics. So in zero shot training, so you know about zero shot, right? We'll be training the model on some data, and we'll be giving the model some new sample, and the model will be asked to predict on that sample, and it actually does perform pretty good on like zero shot evaluation, and also one shot evaluation 31, 5 shot 35, 64 shot 39, and it did beat every model, which is kind of fascinating, because Palm model is actually have like 540 billion parameters, 540 billion parameters, which is very large compared to this Llama. But still, Llama overtook Palm, and it's actually very nice. It's a very good thing. that even with like very less fair parameters, it is able to like beat one of the greatest like huge models, right? um and then zero shot accuracy, as you can see, palm did overtook in one thing. And also closed book question answering, mathematical reasoning, code generation, reading comprehension. As you can see, right, the model has so model data set, the pre-training data set contains data from almost all the sources, like from GitHub, from Stack Exchange, and all that. So therefore, uh, it is it is kind of obvious that it is able to perform different types of tasks, right? So definitely multi-language understanding, right? It is able to understand multiple languages. That is why I think in the last video, when we are building like the chatbot, we have so that the data set is actually filled with multiple languages, and the model was able to do quite well. And it's actually very good. The model is actually understanding not only English but all other languages also. And then instruction fine tuning, I think we'll be going through that also. um and then finally, I just want to show you some examples of performance. We're going down, way down. Right, so as you can see here, they have experimented using some text, and as you can see, if you want to read, definitely go read it. And it was actually quite creative, quite new, quite capturing the patterns of different like funny things and all that. uh, as you can see, if you want to read, please go on. So it is able to generate like scenes. It is able to you know conversations. It is actually able to generate conversations, right? A conversation between sun and Pluto. And yeah, and like bunch of cool things about chess and all that. It was actually quite good. The model is quite good. And again, and considering the size of this model, it's a very small model compared to other models. Let's just see the size of GPT. Oh, 170. Okay, so 1.3 billion, 6 billion, and 175 billion. I think the main GPT-5 has like 175 billion parameters, and Llama has like 70 billion, and which is amazing. And let's say GPT-4. Oh, wow, 1.676 trillion parameters. Trillion parameters. That is quite a big model. But for now, Llama is performing pretty good, considering the like the model parameters. It's like very less parameters, but still the model is able to deliver quite well, is able to perform quite well. And so that is Llama 1.0, the first version. These are the main changes that I've made. And there's also like they have used specific implementation of transformers like called XFormers, right? Do you know like one thing that I will just share with you is that I think it's a pretty interesting fact. In modern GPUs, right? We have modern GPUs, right? In modern GPUs, uh, I think so. Execution memory or execution speed. So so execution. I'll just try to write it here. So execution speed is actually higher than the memory speed. So what that means is, so if you want to, let's say, save a lot of data, let's say you want to save a lot of data, uh, then saving a lot of data is requires higher time than executing that data or executing a lot of calculations. And that is what modern GPUs are able to perform. So let's say of modern GPUs, let's say NVIDIA, Fortinet, and all that. So the execution speed is much lesser. The execution speed is much higher compared to the memory speed, the like storing the memory and reading the memory, writing to the memory, and all that. So that is why I have learned that XFormers is able to use this feature And rather than just storing the attention values, so let's say after performing attention, rather than storing the attention like matrix for back propagation, rather than just storing the matrix for back propagation, in the back propagation, they are going to compute or calculate QKV again. So that is the idea. So rather than just like getting those values and writing them to the memory and reading them out of the memory, they'll just uh, during the feed forward method, they'll just calculate it, they'll delete it. In the back propagation, they'll calculate QKV again and then perform the back propagation. And surprisingly, it is faster. And that is why XFormers in the implementation uses different features like this. And mainly this feature, it uses execution speed rather than just storing it. So bunch of times when we want to store attention weights, right, or any weights, rather than just storing them in the memory, what we'll be doing is we'll be just deleting them and calculating them again. So this is the implementation that XFormers have performed. So therefore Facebook have used them in their implementation. So that is those. So these are the main changes of Llama 1. Thanks for watching, and I'll see you in the next video. So yeah.